this webinar, I will be demonstrating some of the integration among Petrophysics, Geomodeling, and Geophysics, including several new features for the 2019.3.3 release, particularly around the Geobodies and the Geomodel. Today's agenda will include reservoir analysis of the Barnett Shale and Petrophysics to define the target zone. Then we'll highlight the Barnett Shale extents from the inversion volume in Geophysics, followed by creating the Barnett Shale Geobody from the inversion attributes. Then in Geomodeling, we will display the Barnett Shale Geobody in both cross-section and in 3D, and then calculate the length and the percent of the Wellbore and IP tests in the single well Geobody. Then we'll create a survey point report of the Wellbore in the body, and then finally we'll calculate well and zone parameters in the Geobody for multiple wells. We're looking at the Barnett Shale in GVERSE Petrophysics. The orange marker up here is the basal Atoka. The darker blue marker here is the upper Barnett. The light green marker here is the maximum flooding surface in the Barnett. The dark blue down here is the basal Barnett, and then down in here the purple marker, that's the top of the Ellenberger. We're looking at a 6 mineral model showing both the clay content of the shale and the component components. And we see between the maximum flooding surface and the basal Barnett, we're building up some good component components with some native porosity in here and good TOC. So that's probably a pretty good component that we want to target if we have the resolution. Now in the cross section, we're looking at Poisson's ratio, Young's modulus, and in the third dimension in the colors, we're looking at brittleness. So we want to define where we see both the brittle zones and also the ductile zones. So for identification purposes, let's turn on the surfaces. There we're seeing the basal Atoka, upper Barnett, Barnett maximum flooding surface, basal Barnett, and Ellenberger. So let's see where the brittle components are in our data selection. And we'll start by looking at the brittle components, which are plotting down here in the southwest quadrant. And just as we suspected, you do see some brittle components in here between the maximum flooding surface and the basal Barnett that's corresponding to here. But it probably is below seismic resolution to actually discriminate the brittle components from the seismic. So let's see where the ductile components are. Maybe that'll help us with the identification of the Barnett. And now I'm seeing that there is good ductile components, particularly above the Ellenberger to the basal Barnett. So this is a good frac barrier because the Ellenberger is a karsted surface and is a water hazard. So really it looks like that the ductile components are really overwhelming the overall Barnett Shale. So if we're going to be using seismic attributes, we probably want to be looking for something that will show us where we have ductility to indicate where the Barnett is. So that brings us to this cross plot where we're cross plotting acoustic impedance against brittleness. And we see that there is a linear relationship between the two. So if we had an inversion volume of acoustic impedance in our seismic, we could use the acoustic impedance attribute as a proxy for brittleness. And that's just what we did in GVERSE Geophysics. So let's shift over to GVERSE Geophysics. And we're looking at a probe. This is a probe within the 3D volume itself. And this probe is showing the absolute acoustic impedance volume that I generated earlier. Now on the well logs, we see we have the basal Atoka, the upper Barnett, the Barnett maximum flooding surface, basal Barnett, and Ellenberger. So we can see that between the maximum flooding surface and the basal Barnett, we've got good low acoustic impedance, indicating that's where our main part of our shale is. So let's render the volume in 3D. So we're going to render the entire volume. And then we're going to use our histogram over here to highlight only the ductile portions of the Barnett, which are right in here. So we're going to use this little tool here to make the endpoint values transparent and adjust it a bit. So about down to 36, about 0.4, and then the upper one we're going to take down. So we're just showing the ductile components here. So that's very nicely highlighting and delineating between the maximum flooding surface and the basal Barnett. So we're going to create a geobody. We're going to call this geobody the Barnett Shale Geobody. And then we're going to use this paintbrush over here to paint the low acoustic impedance values. So we're going to drag to draw. We're going to draw it right here between the maximum flooding surface and the basal Barnett, over here on the edges of our probe. We're using this as guide components. And finally over here on this side, zoom in for clarity. Paint these over here. Make sure we stay on the edge of the probe. There, now we've defined it. Let's go ahead and generate the probe. And we're going to window in over the time depth interval, which is about 1150 milliseconds down to about 1250 milliseconds. And then we're going to be looking at the acoustic impedance value about 36.4 to a maximum value of about 36.7 or 37.7. I should correct myself. There we go. Let's generate it. So there's our geobody sitting very nicely between the basal Atoka and the maximum flooding surface, defining that zone within the Barnett that we want to target. Now also new for 2019.3 is the ability to create Isomap layers based on the geobody. So that's what we're going to do, and we're going to create a gross thickness Isomap layer. We're going to include color contours, modify the contour interval, and create the Isomap layer. Now we're looking at the map view within GVERSE Geomodeling, and let's display the Isomap of the thickness of the Barnett Shale Geobody on the map. So we're going to select the Barnett Shale Geobody thickness map here, and we'll move it to the bottom of the layering order so we see the wells. So this is the Isomap layer of the thickness of that Barnett Geobody that we generated in Geophysics. So let's turn it off for now, and let's focus in on this well right here, which is this drilling vertical section well. Let's open it up. And let's set up the seismic backdrop. We are hooking into the B-Shale GVERSE geophysics interpretation. For the seismic, we're going to be using the absolute inversion that we used in GVERSE Geophysics. And for the display, we're going to use the same palette that we're using in GVERSE Geophysics that we saw on the 3D probe. And we're going to set the range that we determined over in GVERSE Geophysics of 36.4 up to about 40. And let's turn on the seismic backdrop. Now we see very nicely, again, between the maximum flooding surface, which is that light blue surface, and the basal Barnett, which is the dark blue, the inversions are following very nicely, at least as far as the geomodel is concerned. So now let's add in our geobody. And now we're seeing the geobody right over those low acoustic impedance attributes, indicating the ductility of the Barnett Shale through here. Now we can come in here and look at the properties and adjust the opacity of the geobody. So basically we can co-blend the geobody against the seismic attributes in the backdrop. Now next, let's calculate the length and the percent of this wellbore within the geobody and some test parameters. So we're going to right click on the cross section, calculate cross section, well, and zone. And we have a number of different types of zones that we can calculate. We can do thickness maps, which are basically maps that are defined within the geomodel of GVERSE geomodeling. This one happens to be between the Barnett maximum flooding surface and the basal Barnett. We can take zone manager zones that are actually defined surfaces in the geobody, in the geomodel I should say, and we can take any one of these zones and do the length and percent for those. We can specifically set up upper surfaces and lower surfaces. But for our purposes, we're going to be using the Barnett Shale geobody. And we're going to be calculating it from the top of the zone, in other words, from the top of the body to the TD for the well length, and the test data that I do have available is initial potential. So we're going to be calculating the length and percent of the wellbore within the geobody for the well length and for the IP test. So let's generate that report. And here we see within the Barnett geobody, we have a length of 798 feet, of which the percent of that overall is 35% in zone, and the total initial potential test is 2339, of which 516 in zone, or 23.34% of the IP test is within the zone. We can save this report to any of those zone manager zones I showed previously. We can copy it to the clipboard, or we can save it as a text, either as tab, space, or comma delimited. Now in addition, and this is new for 2019.3.3, we have a survey points report. Now the survey points report will show us exactly where the wellbore is within the geobody. So we have the top and the base of the geobody. We have the thickness, the TVD thickness of the geobody at this particular survey point. Top zone TVD sub C, top TVD offset, top TVD offset percent, zone base TVD SS, base TVD offset, and base TVD offset percent. Again, we can copy that to the clipboard, save it as text with the different delimiters. So now we know exactly where the wellbore is within the Barnett Shale zone. Close that. That was for the single well. Now let's take a look at multi-well reporting. So let's highlight all of the wells here, and we're going to make a 3D well group. And we're going to call this well group the Barnett Shale wells. Add them. And then click on the 3D tab to show the cross section, which becomes a fence diagram, and the Barnett wells. Now let's add the geobody. So we're going to add the geobody. And let's turn on the light for better clarity. So that's showing the Barnett Shale geobody with the wells within it. Now, by affecting the properties of the geobody, in this case we're going to be looking at the opacity property, make it a little more transparent, we can actually now see the well bores that are within the geobody itself. So we may be interested in seeing what is the length and percent of the well bore and any kind of test within this geobody. And again, we can do that now from the map view from these selected wells. We can right click, calculate well and zone for multi-wells here. And again, we've got the possibility of doing thickness maps, zone manager, zone maps, specific surfaces, but in this case again, the Barnett Shale Geobody. Again, the top surface down to TD for the length of the wells in the Geobody and the IP test. And we're only going to be doing it for the horizontal wells, so I'm going to do a multi-selection of just the horizontal wells. And by the way, we can add explicitly based on filtered well lists. In this case, just from a selection on the well. We're going to calculate the length and percent of the well bore in it. Now we have an error report that we can look at. Why did these things not calculate? Well, it will give you an idea. In this case, the IP records weren't found, but for any particular well, you can find out why it did not calculate based on this error log. And again, we're going to be looking at the length and the percent of the well bore in the Geobody for the multiple wells here. And also we can save this out to Zone Manager, copy it to the clipboard to save it as any kind of text. And again, the survey points report is available for all of the wells, but I'm not going to do that again since I did that for the single well. Let's go ahead and close that and maybe put the 3D survey 3D view right next to it. And add back in the Barnett Shale Geobody. And there you have it, integrating seismic geobodies in GVERSE geomodeling. I hope you enjoyed today's demo of the new Geobody integration features between GVERSE Geophysics and GVERSE geomodeling, and the ability to calculate well and zone attributes for geobodies for both single and multiple wells. GVERSE GeoGraphix offers the tightest integration of features among disciplines to facilitate the most productive and sophisticated workflows in the industry today.